Hello world, and welcome back to another math video. Today we're going to be discussing logarithmic functions, just logarithmic functions and their graphs and some of their properties. Let's get to it. So as a warm-up, I thought it would be fun to take a look at 2 to the x. Y equals 2 to the x, or f of x equals 2 to the x. It's your classic exponential function. As with many functions, this function has an inverse. And one thing that we know about this function's inverse is that its inverse is also a function. Can you guess why? How do I know that from looking at the graph? If you guessed it passes the horizontal line test, you would be correct. So let's establish this inverse. So one way to do that would be by making a little table of values. Simple table of values. We've got x and y. Let's go -2, -1, 0, 1, 2. And if I plug in -2, I'm at 1/4. Then -1 is a half, 0 is 1, 1 is 2, 2 is 4. Okay, and you can see these values are here. At -2, I'm at -1/4. At -1, 1/2, 0, 1, and then 2, I'm up at 4. I mean, we can keep going with this one, but I think we're pretty good with those values. And if you want, fine, since you insist. If you plug in 3, you get back 8. See, look, 1, 2, 3, and then we're up at 8 there. So who remembers how to graph an inverse given a set of points? If you guessed, just take all of the x and y values and exchange them so y becomes x and x becomes y, you'd be correct. So the inverse, we have x, we have y. So I'm going to just write all my x values in the y column. -2, -1, 0, 1, 2, 3. And then 1/4, half, 1, 2, 4, and 8. I'm going to plot those coordinates. So when x is 1/4, y is -2. X is 1/4, y is -2. When x is a half, y is -1. When x is 1, y is 0. X is 2, y is 1. And when x is 4, y is 2. And when x is 8, y is 3. So that's interesting. And then we're going to just take those values and I'm going to connect them. Now I'm bringing some prior knowledge to this situation. But one thing that we also do know about functions and their inverse is that they have symmetry with the line y equals x. So if I were to just go ahead and graph the line y equals x, you could see that that function, the blue function there, tends to have some symmetry. Now, I mean, it has lots of symmetry. It's perfectly symmetrical with the line y equals x. All right, so inverse functions have symmetry with the line y equals x, and all of their coordinates are x and y exchanged. If you're wondering what function that the inverse function that I just graphed is, we would know that as f inverse, in this case, is going to be log base 2 of x. Okay. Now, if you look at the function, you can notice that like the exponential function, there's also an asymptote for this one. With the exponential function, the 2 to the x power, there's a horizontal asymptote on the left end, right? It's y equals 0. Notice here we have a vertical asymptote at x equals 0. Like y and x got exchanged again. It's almost like every single thing that was an attribute for the exponential function is now an attribute for the inverse, except you just exchange x and y. All right. So that's the log. So we have log base 2 of x. Notice again, I have to jump back here, that the base here and the base here are the same. Okay, they must be the same if they're truly going to be inverses of one another. So here on this particular slide, they say changing between logarithmic and exponential form. So I'll take you on a tiny little journey here. It's just worth noting. So say somebody said, hey, we have this function, 2 to the x. Can you give me the inverse to that function? So the first move you would make is you would just take x equals 2 to the y value. Okay, so that is what you would call the implicit inverse. It's implied, it's like implied to be a function or whatever, but it's automatically that. So just for giggles, let's jump over to here, and we have y equals 2 to the x. Whoops. 2 to the x power. And I just showed you that we know that the inverse is y equals log base 2, but we could also just go like this. X equals 2 to the y power. And this calculator is smart enough that it'll actually, in fact, graph exactly the inverse. To prove that to you, on the same set of axes, I'm also going to graph y equals, and then just go to this log base function here, go log, and then it's giving me the option there to plug in the base 2 of x. So as you can see, it graphed it right on top of that blue graph. So the green one is exactly the blue graph. They're talking about exactly the same thing. So how is it that we have this other notation log? Well, just like when you go to solve any equation, right? Like our job right now would be to solve for y in terms of x, because now we have x in terms of y. That's not good. We want it to be an explicit function. We want y equals and then everything else in x. So if you recall, when you learned about inverses, there's this inverse property. For functions. And that is f of f inverse of x so f of f inverse of x, if you compose them, that's going to equal x, right? So when you apply an inverse to a function, it just leaves you with x. So, and vice versa too. If I were to just take this and put the inverse there, I'm also, if I did f inverse of f of x, the inverse property should apply as well. For all the values that are in the domain, we're good to go. Okay, so that would be that'd be that. So so why am I showing this to you? Because the word logarithm, actually, I'm not saying it like its Latin roots or means inverse of exponential, but in mathematics, the log function is used as an inverse operation to an exponential function. So if I want to get y by itself, then I have to apply the inverse. And the way I would go ahead and apply that inverse, so I'm just going to slide this over a little bit more, is I'm going to take the log base 2 of both sides. Because I know that log base 2 of 2 to the x, or 2 to the y in this case, because they're inverses of one another, because these bases match, this would go away and leave me with the argument, which is y. So now I have y equals log base 2 of x. This is equivalent to x equals 2 to the y. They're both exactly the same thing. They mean the same thing, as demonstrated in Desmos over here. I did it with base 2. As long as the bases match, that's cool. So that's how you can convert between the two. So if you have y equals log base b, some generic b of x, that's logically equivalent to b to the y equals x. Okay, so you can exchange them and use them how you will. So when you're graphing, typically your y equals, but if you're solving some other, if you're using it for some other situation, you would maybe convert it to exponential form. Now, one thing worth noting the base here, this b, abides by the same rules as an exponential function. So if I have like y equals b to the x, right? We know that the base is greater than 0, and the base does not equal 1. Has to be. Okay, those are the rules. This is the exact same base here. So you have to acknowledge that. Most likely it's not going to come up anyway, but those are the rules. So they note here that the way they wrote it here is b is greater than 0 and not equal to 1, but they just wrote it in that form. It's a little bit odd. It's peculiar. And also they're noting that x, the argument, has to be greater than 0, which totally makes sense because for a couple of reasons. One, again, if you look back at the graph of this parent function, log base 2 of x, notice how the domain is x is greater than 0 here. And how do you know that? Well, if you, again, another fun property about inverses is the domain of an inverse is the range of the original function. So if you look at the range of the exponential function here, that red one, the range of that function is y is greater than 0. So again, x and y got exchanged. So that's what's happening. So that'll come up again, but just worth noting now. All right. So yeah, it says here on the slide that the functions y equals b to the x and y equals log base b are inverses of one another. Okay. So and being inverses, all of the properties of inverses come with that. So, all right. Now there's two other log functions that are worth noting. The natural log, that's ln, that's how it's denoted. So you could always write the base in that base position, right here. But because the natural log and actually the common log, both e and 10 respectively, they're used so often that they both got their own like version of log. Ln implies that it's just log base e. It's still a log function, looks very similar to the other ones, but it's base e. And then log by itself, when you don't write a base there, just use the word log, it's implied that it's base 10. Okay, so common log, just this log, when there's no base, this means it's base 10, and natural log is base e. And you do need to know that distinction. So if you're writing log base e of x and you're taking a calculus class, the teacher or whatever class, they're gonna have a talk with you and ask that you use the proper notation. All right, moving on. So using this whole just changing between log and exponential form can help us to evaluate logs, right? So if you wanted to know what log base 2 of 16 is, right, because it's a log function, so we would want to just get ourselves in the right frame of mind for like what does the log actually mean? What is it giving us? So of course, since we don't know what that is, I'm just going to use the variable x just to make it easy on ourselves. So we want to know, what does log base 2 of 16 equal? So if we convert this to exponential form, this could be written as 2 to the x equals 16. Then you're like, oh, 2 to the x equals 16. I know my powers of 2. That means that x equals 4. So when you go to evaluate this log, actually, I can just go right over here now and just say log base 2 of 16 is 4. So you could check that on a calculator. That's another thing, but just how to do a log base on a calculator. But anyway, moving on. Next one, log base 3 of 81 equals. So a log is the solution to a missing exponent. You're usually using logs to solve for unknown exponents, as indicated here. I'm going to let this one equal a. So that means 3 to what power equals 81? Well, we know 3 squared is 9, 3 cubed is 27, 3 to the 4th. So this time, a equals 4. Once again, 4. And I just thought I do have a calculator on here that will allow me to change the base. This handwriting one. So let's go log base 3 of 81. It's going to give me a hard time. 3. There we go. So, and you can see log base 3 of 81 equals 4, as we discovered. So why don't you try out the rest of these? and we'll check back in a second. I'll just write the answers in. And this one's interesting, this last one, because that one is actually starting out as an exponential, and you need to turn it back into a log. So here you'd be like, all right, I'm going to just let this equal x. So how do I get this back into logarithmic form? Well, I think it's probably, it's kind of hard for you to see this, but it's going to be, I'll write the regular model over here. So we know that b to the y equals x, and log base b of x equals y, right? We know that these mean exactly the same thing. So if we use that same logic, that means that this would be my y value, right? And I still have my x value over there. So if I let y equal that exponent, that's in terms of logs, all I need to do then is write log base 6 of 5 in the y position, and log base 6 of x in the other position. And you can see that they're both log base 6. One has a variable, one is a constant. So we know that we're just going to have to, we can set those two quantities equal to each other, right? Log base 6 of what equals log base 6 of 5? X would have to equal 5. The other thing that we haven't really discussed very much, I mean, I've talked about it, is that this is actually a composition of two inverses. Here's a base 6 and then a log base 6. So this is a composition. So they actually, in fact, cancel each other out, and you're left with 5. I don't want to spend too much more time on that. I think that's something that you'll explore more in the future. All right, let's talk about graphing logarithmic functions. Notice I say sketch the graph of. I decided I would just make one up as I go along. Sometimes when I try to find problems in the book or whatever, they're limiting. But I want to just demonstrate how to establish a parent function, and then once you have that, how the rules of transformations just apply. Like they're the same as they've always been. So I'm going to say sketch the graph of, and we're going to go with, I don't know, let's go 2 log base 3 of x minus 3 plus 1. Okay, so 2 times log base 3 of x minus 3 plus 1. So if this were just any function, right? Just we don't say you don't even know what log looks like yet. What we do know is that after we graph the parent function, the first thing we're going to do is look for any form of multiplication. Nothing's happening in front of x, there's just a 1 there, but there is something in front of the function. So I'm just going to note step 1. We're going to take all of our x, y values, and we're going to scale all the y values by 2. So this is just a coordinate notation for transformations. This is for technically a dilation. It's stretching only in one direction. It's actually not even a dilation. It's a it's a distortion. I mean, part of it's being dilated, but it's not going to be the image of this is going to be distorted. It's a stretch only vertically. So it's a vertical stretch by a factor of 2. So that's just the notation for doing that computation. So once you establish those parent points, you're just going to take only the y values from that parent and multiply them, double them all, so you're going to stretch it up. And then after that, step 2, we can combine these two moves right here. That's going to tell us to go right 3, and this is going to tell us to go up 1. So I'm just going to write right 3, up 1. So now we have that. So fantastic. All right, and then so let's actually figure out that parent function. So the parent function is going to be y equals 3 to the x, right? I'm sorry, I'm not telling the truth exactly. Log base 3 of x. So how do I establish the key points for that function? Well, since you asked, there's a couple ways to do that. One would be making an xy table off of the exponential form. So we could just say x equals 3 to the y, and we want to plug in values that are convenient for us to evaluate. Well, if I would like to look at when y is equal to -2, -1. Well, actually, y can't be. No, I'm sorry, it can. 0, 1, 2, right? And if y were to equal -2, x would equal 1/9. If y equaled -1, x would be 1/3. If y equals 0, x is 1. If y is 1, x is 3. And if y is 2, x is 9. Which totally makes sense. Should sound a little bit familiar. It's just an exponential function, instead of I'm doing it in reverse. I'm plugging in y values to get x. It's easier to raise 3 to a whole number power than it is to some kind of fraction power, especially if I'm graphing by hand. So those are the values I'm going to use. So now I can go to where x is 1/9 and plot -2. X is when x is 1/3, plot -1. When x is 1, y is 0. When x is 3, 1, 2, 3, y is 1, and x is 9, 4, 5, 6, 7, 8, 9, y is 2. All right, and then we can just take that function, and we could lightly connect the dots. I'm actually going to use a highlighter just to give you a sense for what it would look like, but this is not our final graph. So that's pretty much, that is the parent function. Now, when we go to apply our transformations, we have to multiply. The first thing we have to do is multiply all the y values by 2. So I'm going to graph my final graph in red. So anything that's that's a y value, x is going to stay exactly the same. This first one, y is -2. When I multiply that by 2, it's going to go down to -4. -1 goes to -2. 0 stays. And 1 goes to +2. And 2 goes to +4. And then what I'm going to do is I'm going to wipe out the first function and reconnect the dots. And I'm going to reconnect the dots with my red marker because I can just do a transformation now on what I have here. And we know that it takes off and goes like that. Notice how I'm snuggling up to that vertical asymptote at x equals 0. All right, so the last move is to take all of my key points and shift everything to the right 3 and then go up 1. So 1, 2, 3, and then up 1. Now, because it got moved right 3, I'm actually going to draw in green my vertical asymptote that was the y-axis. X equals 0 was a vertical asymptote. And because everything went to the right 3 units, I am going to just take that and go 1, 2, 3. Because when x is approaching 3 from the right side, y is going towards -infinity. That's a vertical asymptote. So there you go. So now let's state the domain. Let's get rid of all this stuff because we're done with it. All right, so let's look back at the original function. The original function says that. Now, one thing that was stated at the beginning for logarithmic functions, the argument must be greater than 0. Okay, so again, the parent function log base 3 of x, okay, equals like y, y equals that, or we'll just say equals y. If you think about it, this cannot be negative, because the other way to write this is 3 to the what power equals x. So I can't raise 3 to any power and have it become 0 or a negative number, right? So x would have to be greater than 0. And that's why the domain for all log functions is strictly x is greater than 0. So what does that mean for this particular scenario? Well, this scenario, the argument is x minus 3. Algebraically, you can always find the domain for any function. You don't have to look at the picture. So actually starting out a problem like this, I would have suggested state the domain first. If you state the domain first and then go and graph it and then look at your graph and compare it to your domain, then you'll know if you're on the right track. So the way you would go about finding the domain for a logarithm, and this is for any logarithm, is it doesn't matter what's on the outside of your argument. That has no influence on your domain. This right here, whatever's inside the parentheses, you take that and you say, what is x if this is greater than 0? You have to solve that inequality. So this is a nice simple inequality. Add 3 to both sides. X has to be greater than 3. So that means our domain is 3, infinity. All right, so that's how you do it. It's reminiscent of a square root function, except that you don't include the 0. Where it equals 0, not good. Can't be 0. All right, strictly greater than 0. All right. The range is something that you need to look at the graph for, but the range is actually always going to be all real numbers. Okay, you can see that there. Intercepts. That's interesting. I'm going to hold off on intercept right now, only because, I think you can see where the intercept is there. This function did get shifted. Yeah, we're going to hold off on that because we don't really have the tools yet for solving these. So I would want to do that algebraically. But you can see where the x-intercept is, and there is no y-intercept on this one. Okay. But if you're asked for x-intercept, you absolutely could set it equal to 0 and solve. All right, so there's that one. We're at almost half an hour. So I had ambitions of doing 3 of these. So why don't we skip down to this one? Because I think that you could probably extrapolate how to do, pretty much any other graph of a log function based on that example that I gave you. I just wanted to talk about the natural log function, ln. So if somebody were to ask you to graph like g of x equals, let's say, negative ln 2x and then plus 4. Okay, this is just another log graph, and as long as you know how to do transformations and establish a parent function, it's just going to be more of the same. All right, so first of all, let's establish the domain for this. So my argument 2x has to be greater than 0. That means that x is greater than 0. So yeah, this is 0, infinity. The range is going to be all real numbers because even though normally you need to look at the graph, it's a logarithmic function. Its range is all real numbers, so that's good. Don't worry about intercepts. Oh, asymptotes. On that last one, I did ask for asymptotes. Could you please state that x equals 0 is a vertical asymptote? This one is going to have a vertical asymptote. Again, there are no horizontal asymptotes for logs. At this one's x equals 0. All right. So how do I establish my parent function? Let's the parent is going to be y equals ln x. Okay, so we'll look at that. So if it's y equals ln x, let's make a little table. Actually, before I make the table, let's go rewrite that as x equals e to the y. And then you should remember from the video on graphing exponential functions that you can just plug in your 0, 1, and 2 values. E to the 0 power is going to be 1. E to the 1 is 2.7, and e squared is 7.4. Again, these are approximations. So that means for ln x, if I plug in 1, I get back 0. If I plug in 2.7, 2.7, I get back 1, and 7.4. 1, 2, 3, 4, 5, 6, 7.4. I'm up at 2. All right, so that's the parent function. And then I'll once again use a highlighter to just indicate, just to give it some shape. But it looks just like any other exponential function. Now, certain things I didn't note earlier, but we'll just point it out now. All exponential functions have the point 1, 0. want you to think about that, and you can get back to me telepathically. All right. So that's just like 0, 1. Flip-flop those points. All logs have 1, 0. All right. So let's mark up our original. So what's interesting here? Let's look at some multiplication. All right. Out front, we do have some multiplication. So we're multiplying all of our y values of our parents by -1. That means to take the parent and reflect in x-axis. Okay. Step 2 is going to take that function now that we just reflected, and then we're going to multiply all of the x values by a half. So that's going to say take x comma y, all the from the prior stage. That's how I work this. And we're going to take all the xy's from the prior step, and we're going to multiply all the x's by a half and leave the y's alone. So it's going to be a horizontal compression by a half. And then lastly, the last step, move that up 4 units. All right, let's do it. Okay, so first thing we're going to do is reflect it in the x-axis. So that green point there, the first one, 1, 0 stays. 2.7, 1 goes to -1. And then the 7.4, 2 goes to 7.4 and -2. Now it's upside down. So I can take these, make those gone, highlight. We'll highlight in this kind of greenish color. Snuggle that asymptote, and all right, so we're dealing with that now. And then we have to take all of our x values and multiply them by a half. So half of 1 is 1/2. Half of 2.7 is going to be 1.35. Just going to double check on that. 2.7 divided by 2 is 1.35. I was pretty sure, but 1.35 goes right there. And 7.4 divided by 2 is, I think I had it written here just a moment ago, 3.7. So it's going to be 123.7. So yeah, there's quite a bit of horizontal compression there. And then I'm going to take this original out, and now I'm going to highlight in the final graph color. And the reason I'm committing now is because the rest is just going to be a rigid transformation, aka well, that's a type. It means it's not going to change in its scale or stretch or flip or anything. Actually, even flipping would have been okay, but this is just going to be a translation. And the last move is go up 4 units. So I'm going to take this entire graph now. I'm just going to go leave everything where it is, but just go straight up. 1, 2, 3, 4. And there it is. I didn't have to move my vertical asymptote. It stayed where it was, and this is our new function. And it does appear that on these logarithmic functions that there's a horizontal asymptote. There is not. There is a range of all real numbers. It tends to either increase or decrease very slowly. So anyway, there is that. Hopefully that was somewhat enlightening to you. And the last thing I wanted to do is just practice evaluating some more logs. So why don't you just take a moment and evaluate all these, and then we'll check back in a sec. I'm just gonna just rapid fire write these answers down. So why don't you just pause the video and then do this, and we'll call it a day. All right, 2 to the watt power equals 8. That's 3. 3 to the watt power equals the square root of 3. That'd be 1/2. 5 to watt power equals 1/25. That would be -2. 4 to watt power equals 1. That's 0. 7 to watt power equals 7. That's 1. They want us to think about this. 2 to watt power equals 0. 2 to watt power equals 0. That doesn't happen. So impossible. And also that violates our domain rule. Likewise, say this is like A. 2 to watt power equals -1. Again, that's impossible. So these yeah, we're thinking about it. Both of these violate that domain that we spoke about before. So the domain for any logarithmic function must be greater than 0. And that's why. All right, moving on. So these are somewhat designed to be tricky because they're all invisible base 10. Okay, so again, 10 to what power equals 10? 1. 10 to what power equals 100? 2. 10 to what power equals 1,000? 3. 10 to what power equals 1/10? 0.1, it's -1. 100th, -2. 1,000th, -3. Okay, so you can see that it's not too bad for evaluating logs of bases where their arguments are typically some kind of a power of that base. So they get more complicated, but these are the basics. So hopefully this video was helpful to you, and hit me with some questions if you have them. Take care.